Dr. Jensen. Today my topic is investigation of mass transfer in gas shale. As we know, natural gas is one of the most important energy resources in the world. And it has two types of, we can produce from two types of reservoirs. One is conventional reservoir, and the other is unconventional reservoir. And the difference is that unconventional reservoir has a large volume but lower permeability compared to conventional reservoir. As the demand and supply gap of natural gas increasing every day, there is an urgent that we need to find a way to extract the unconventional gas resource. Most important is we need to find a way to extract gas from shale gas. Why? Because from here we can see shale gas counts for around 50% of the total unconventional gas resource in the world. So if we can find a way to optimize the production from shale gas, we will make great contribution to the world energy issue. Right now, as shale gas has very low permeability, so people have to find various methods to extract it. Right now, people have to use hydraulic fractures here to manually create fracture network to stimulate the production. Here's an example. I use a tree to illustrate the fracture network. The trunk of the tree is like the major fracture, and it has branches and smaller branches, and even smaller branches. So the natural gas in the reservoir has to travel from the micro fractures to macro fractures, and all the way to this trunk, which is the major fracture, and to be produced. So, if we can understand how the gas travel and the mass transfer mechanism of the shale gas travel through those fracture network, we will be able to optimize the production rate, right? Imagine this. When gas being produced through this path, the gas pressure will decrease, but the formation pressure remains the same. What does it mean? It means the net stress that acting to the fracture increases. We all suffer traffic in LA. Imagine we have a 5-lane freeway, and when we suddenly make the 5-lane freeway to 1-lane freeway, it drives us crazy, right? So if we want to have more gas coming out, we have to slow down the compaction process so we can have more gas coming out. In order to solve the problem and increase the production, here's our experimental sample. This sample has fracture network, and which is extracted from 8,000 feet underground. We want to use this sample to investigate the compaction effect. Here is our experimental setup. We put our sample in this core holder, and this one is a hydraulic pump, which we can provide the confining pressure to surround the core. And we have this back pressure regulator associated with it, pressure transducer. We can provide a fixed back pressure, which is like the well-bore pressure in the reservoir. And we want to have different back pressure but the same pore pressure and the same confining pressure. So we can inject the gas. Here's the upstream system. We can provide the core with a certain pressure, for example, like 2000 psi. And we can set various back pressure. So when we open this valve, the gas will deplete from the core sample to this downstream system. So when we do that, we have different back pressure, so we have different pressure drop. So the net stress increasing rate is different, which means the compaction rate is different. For example, like currently people produce gas like from 5-lane freeway to 1-lane freeway. We want to investigate whether we can produce like the traffic from 5-lane freeway to 4-lane freeway and to 3-lane freeway. We slow down the process and we maximize the gas production. Here's our experimental terminology. And first, the pore pressure is the pressure we use our system to inject the gas into our sample. So it's like we mimic the reservoir situation. And we have confining pressure, which is similar like the formation pressure. So finally, we have this back pressure, which is the reservoir wellbore pressure. So if we can control the reservoir wellbore pressure, and we deplete the gas to it, and we have different wellbore pressure, so we have different compaction rates, that we have a different production rate. Here's the experimental parameters. We have the same pore pressure, which is the gas pressure in the reservoir. Then we define same confining pressure, which is the pressure on formation, but with various back pressure, which is we control the downstream pressure. Here's our flow rate under different back pressure. This is what we want to observe from our previous hypothesis, because different back pressure results a different flow rate. That's very important. If we can find out the optimum flow rate with a certain back pressure, we can optimize the gas production. So these are the maximum flow rate versus back pressure we observed from our previous experiment. We can see that with back pressure increase, the maximum flow rate increase, and then it decreases. What does it mean? Imagine we have this initial pore pressure, and we decrease to different back pressure. First, we have the different driving force, because gas can be produced because it has driving force. It drives the gas out, right? And next, second, we have this compaction, which is the shrinkage of the formation. So these two forces reaches an optimum point, which is around 750 psi. It provides us the optimum production. So from our experiment, first we know that production rate is sensitive to compaction, because we see from the previous slides that different back pressure results in different flow rate. Also, gas production is controlled by two forces. One is compaction force, the other is the driving force. And also, from the previous slides, we see there is a peak. There is a peak of the maximum flow rate, which means if we can find the optimum wellbore pressure in the reservoir, we can maximize the production of the shale gas. So in the future, we want to repeat the experiment with a different sample to confirm our observation. And second, we want to measure the permeability under different confining stress. And finally, we want to build a model to mimic our experimental setup. And right now, our preliminary results has already been submitted to Energy Corporation of America for field test. Thank you very much.
There's time for a couple of questions.
Your experiment was essentially steady state, right?
What do you mean by steady state?
It wasn't a function of time.
Yeah. We calculate flow rate as pressure versus time. Yeah. We calculate because we have this sample and we have this downstream system. This downstream system has much larger volume than this core. So when we deplete the gas from the core, and we record the pressure here. So the pressure will change with time. So we can calculate the flow rate change with time. Because it has very large volume, so the pressure increase in the downstream remains relatively the same, but we still have pressure change. So we can achieve two things. First thing is we can achieve the certain back pressure. The second thing is, because we still have pressure change, so we can calculate the flow rate, use that pressure.
All right, let's take one more question. Go ahead, please.
Okay, I can speak loud enough. So 750 is the back pressure that you have.
No, it's just for this sample at 2,000 psi pore pressure.
Did I finish my question?
I'm sorry?
Let me finish my question.
He needs to finish his
Let
question.
me finish my question.
I'm sorry.
Number 750 back pressure that you calculate, is it not tied to the difference of the two initial pressures? And if so, what is the general formula? Or is it that this is just one numerical result for one condition?
I'm sorry? I didn't hear it.
The pressure, the 750, is it tied somehow to the differences in the pressure, the confining pressure and the pore pressure?
Yeah, it does differ. Because when we change that, we will change because this 750 psi optimum back pressure is just for this, because it's just for this pore pressure and this confining pressure. So if we change the condition, the driving force is different. So the net stress changing rate is different. So we will have different result.
Let's take Arthur one more time.